Welcome to another Lightblade Learning Lab. Today I hope is going to be a very interesting session. It's going to be packed with lots of tips and features and some very important facts about the machine itself. Now, before you get started, I don't want you to fall asleep. I would like you to put this on pause for a few moments, go and get yourself a cup of coffee, and while you're about it, can you hunt down an old style wooden pencil with a lead sticking out the other end, and make sure it's nice and sharp, and then come back and we'll restart the session. Great. Well, hopefully you're now going to be fully aware, because we said we were going to start benchmarking the machine. Now, there are many different ways where we can start benchmarking the machine. Benchmarking basically means putting a peg in the ground so that we know what the performance of the machine is now, because in 6 months time, 3 months time, whenever, our machine might degrade, and it would be good to have the tools to know that the machine is no longer in tip-top condition. And you can either have a go at fixing it yourself if you feel confident, or if you've got the right tools to demonstrate that something has changed seriously, you can probably call Thinklaser in and they will fix the problem for you. Okay. We could start at the laser tube end. We've already discussed the laser tube in quite great detail, so you know how important it is and how it works. Once the laser beam comes out of the tube, it has to pass around the machine via a series of mirrors. Now, the mirrors themselves we've touched on a little bit with reflectance and the danger of the beam, etc. We're going to concentrate on mirrors in a completely separate session, because they're a big subject all on their own. And then finally, we've got to get to the lens. Now, the lens is the most important part of the system, because without the lens, you don't have a useful machine. So today, what I'm going to do is concentrate on trying to give you a conceptual understanding of what this lens does, and an understanding of why you've got 2 or 3 or 4 different lenses with your machine. There may be some of you that never did any science lessons. There may be some of you that did attend science lessons, but at the point in time when the science teacher was trying to teach you about optical paths and bits of glass and bending light, your hormones were probably to the fore and you weren't really interested. You were more interested in the young lady at the back. Let's just start off from square one and give you 1 or 2 very basics about lenses, because the way that I want to describe them to you hopefully will be memorable. Now, I've got a picture on the screen here of 3 lenses. Now, they all look the same because that's just my laziness, the way that I've drawn them, but they have got something called a focal length. Now, depending on the shape of the lens, the laser beam comes in from the top as a parallel beam, it passes through the lens, and then its shape changes. Now, depending on the focal length of the lens, and here I've shown 3 different focal length lenses. We've got a 1.5 inch lens, 38mm, a 2 inch lens, which is 51mm, and a 2.5 inch lens, 64mm. Now, each of those lenses has got different properties. The key property is the size of the dot at the focal length. Now, that determines something called the energy density of the beam itself. Now, I don't want to go into too much detail on energy density at the moment, but you'll hear me using this word energy density quite a lot. And it's very important that you understand what energy density is. Now, did you get that pencil I asked you to find? Well, if you did, then what I'd like you to do is to pick it up and with the blunt end of the pencil, push it into the palm of your hand as hard as you can. You can do it very hard and it doesn't hurt. It might make a little mark, but it doesn't hurt. Okay, now turn the pencil round and cautiously press it into the palm of your hand, point first. Now, I guess that it isn't going to be very long before you say, oh, I can't do that very hard. Okay, if you were to apply the same amount of pressure that you did when you were pressing the blunt end in, you'd probably push the pencil right through your hand. What we've done, we've concentrated the energy that you have applied to that pencil into a very, very small area, i.e. the point. And you can do a lot of damage with the point, but you can't do much damage with the blunt end of the pencil. Now, the key word here, damage and energy density, sit side by side, and that's what I want you to remember. Energy density equals damage. So the lower the energy density, the less damage you're going to do to the material. Okay, that's an important lesson about the concept of energy. And bear in mind that this energy that we're firing at this lens is invisible. It's not light that you can see, it's actually heat energy. We're concentrating this energy, this heat energy, into a very, very powerful beam. And at the focal point, it's able to do a huge amount of damage. Okay, so the focal points, we've got 3 different focal points here. Why do we need 3 different focal points? Well, if we take a look carefully at the shapes of the paths that the beam is taking, you'll see that the 38mm has got a wasting. It doesn't actually, the beam doesn't actually cross over and come to a real sharp nothing point. It has some spot size right at the 38mm dimension, and it comes in and out very quickly. And I've drawn a dimension in there, 14.662. That's rubbish. Basically, it's more like, in the real world, it's more like 1.4mm. In other words, plus or minus half a millimeter. That's what they call the usable focal depth. Now that basically means that the energy density is approximately uniform over only 0.7 of a millimeter above and below the focal point. So you have to be very accurate with your focusing to get the best out of your beam. Now when you get to the 51mm 2-inch lens, you'll see that 1.4mm, and let's divide the numbers by 10, has changed to 2mm. So we've got plus or minus a millimeter now. We've got a little bit more flexibility in the range that we can use the lens. And then we've got the 64mm or the 2.5-inch lens, and you'll see that that's gone up to 2.5mm. We've got an even wider range of operating. For instance, the 51mm lens has got less energy density than the 38mm lens, and similarly the 64mm lens has got less energy density than the other two. If you want to do the same amount of damage with a longer length lens, you have to have more powerful machine. Now, these are concepts which I want to deal with in another session completely, all about energy density and the way in which you could use your lenses. Today I want to purely talk about the focal length. And what I've tried to describe there is the usable focal length changing, and why it's important to make sure you get your lens set correctly for the focal length on the job that you are doing. So this is not a subject that we can just pass over. You need to understand about lenses. Now the machine has got an autofocus system on it, so I want to tackle the problem from the grassroots section upwards, and then we'll work back into the autofocus system. Okay, so we've got to do 2 things when we get to our machine. We've got to establish what focal length lens is in the machine to start with, and secondly we've got to establish whether or not the machine has got it set correctly, i.e. if it's a 51mm lens, is the lens set 51mm above the workpiece? That's important. How do we do that? Well, I'm afraid there is nothing really on the machine that allows you to find that out. You could play around for ages with the spot size and see if you can get the thinnest possible line. We're going to use this session again to make another very useful tool that will help us determine exactly where the focal length is for the lens. Now what we've got here on the left are some paper targets, and in the first instance we don't need those. As I said, I always put my designs together in one DXF file so that we can import them all at once. So first of all, we'll delete the half that I don't need. And then we'll also delete the material, which is 5mm acrylic. And I showed you how to cut vector text last time. Equally well, what we could do, we could put this on a separate layer. And first of all, we'll group it. Very important this, keep grouping things. Because now all I've got to do is touch on one part of that and it brings the whole lot up. And I'm going to put that onto a blue layer. And the blue layer, I'm going to turn this blue layer this time, instead of a cut layer, we're going to turn it into a scan layer. So this is our first introduction to engraving. You'll notice that I've got the text backwards. That's because I'm going to engrave and cut from one side of the job. But that side of the job is actually the back side of the job. So I'm going to engrave on the back of this acrylic so that when you look through it from the front, you will see a nice piece of white text. And for engraving, you will always need to be running at high speed. Now, 200, 300, 400, it makes some difference, but not a great deal of difference. The main difference it will make is to the depth of the cut that you will achieve. So I will leave this at 200. And power, well, I would think we probably need to push the power up to maybe, I'm guessing, let's just say 20%. I'm going to put these numbers the same. And down here we get other options which appear. Until we talk about it otherwise, leave overstriking as unprocess and leave scan mode as X swing. And that's all we need to do. So we're going to cut 5mm acrylic. Let's set the parameters for cutting. Speed, difficult to say on this machine. As I said, I'm guessing because I haven't got much experience with it. Let's play safe and go down to as little as about 8mm a second. And 67% power, which I've already used elsewhere, which is the maximum I can use for this machine. So all we've got to do now is to decide how we want to order the cuts. Now, here's where I'm going to show you a few more tricks over and above what I've already shown you. What we've got to do is probably engrave it first, then cut the holes, and then cut the outside shapes. That's the order that we've got to think of. But what I'm going to do, I'm going to grab hold of all of the holes there to start with, and they will turn into a red group. But hang on, I've also caught focus ramp as well. That's turned red. And I don't want focus ramp in that group. So what we do, whereas up to now I've shown you how to add things to a group by holding the shift key down. Press the shift key down and touch on focus. And now we've subtracted focus from the group. You can now let go of the shift key and we'll go up there and we'll group. And what we've grouped is just the holes. So you can use your shift key for additive or subtractive grouping. Okay, now in the same way, we can just grab the whole outside shapes like that, hold down the shift key, touch on a ramp, touch on a hole, grouped. So we don't have to collect the pieces individually additively. We can also collect the pieces by subtracting something from the whole. Now that's quite an important time-saving trick sometimes when you get very complex jobs. Or when you've selected something wrongly and you want to subtract just one or two items from that grouping. I'm going to save this as focus 1. Nice short name, but I've got another focus file to come out as well. So we'll save that as focus 1 onto the memory stick. Have a good day. Thank you. And this is another trick now. We really need the other part of the file to do now, but we could marquee this, clear the page, delete it, and import it again. That's tedious. Look, let's just do Control Z. 1, 2, 3, 4, 5, 6. We can go back quite a long way with Control Z, and we can get back to the beginning of our import file. And now we can do the opposite. We can delete the bit that we don't need, which is that bit. We delete the frame and we delete the card specification. Now what we've got here is scorched text on a piece of card and an outside shape. Now the outside shape, again, let me just show you, has got a gap in it at the top and at the bottom, so these pieces remain attached to the card. It looks very complex to program this. It's not, because first of all we're going to do this, and I've captured all the text. We'll put that into a group and put it onto a blue layer. Now the blue layer is going to be a cut layer, so we need to make sure that it's cut, but we're not really going to cut it. What we're going to do is scorch it with cut lines. So we're going to cut poorly, basically, and we're going to do that by taking the power down to something like about maybe 10%. Very, very low power, as low as we can get it. And the speed, well, we need the speed quite high. We try it at 100 because we don't want to burn through, we just want to scorch the surface. And now the outside shape. Well, we've got to cut the outside shape. Oh, that's only one of them. How do we collect the outside shapes? Well, go back to our trick, collect everything, hold down the shift key, and then click on the blue layer, and it's gone. So now we've just got the outside shapes in a couple of clicks, and we can make those into a group. We click on the black group up here, double click, and we can set the cutting parameters now for cutting these shapes out. Speed, I'm going to set that to something like about 50 millimeters a second. Normally I'd run that at about 100, but I'm going to say 50 millimeters a second, and we probably only need 20% power. So we've got to do the scorching before we do the cutting, but remember we've only got two groups that we've defined on here, so we don't need to do very much other than come up here to our edit cut property, and look, there's our two groups. Dead simple. We want that cut first, and then we'll do that element there. So we now save that to a U file as well. Okay, now you will remember when we were here last time that I was commenting on the fact that I thought these cuts were very wide. In other words, the beam was cutting far too wide. Well, that's probably because it is out of focus. As I've just shown you on the picture of the beam, if you move away from the true central position, then the beam starts to get bigger and the energy density starts dropping off, so that means your cut is not as good or as efficient. So what we're going to do now is to make a piece of tooling to check that. One of the great advantages of having an autofocus system, although not necessarily the pen, is that when we get it working properly, and at the moment it's not working properly because I don't understand how to use it, but I will find out, we ideally need to do our engraving on the surface, but when we come to do the cut, this is 5mm material. The ideal place for the focus point when we're cutting this material is going to be 2.5mm into the surface to get the most effective cut. We're not going to do that today. We're just going to stay with the focus on the surface, more or less. I think the focus is actually about 1mm down into the material, but it's a compromise that I'm using today. Just check that it fits on the material, which it does. Air supply on, extraction on. Now this is engraving, and it takes a long time to do engraving because there's this scanning action that takes place backwards and forwards. And that's why quite often it's actually quicker if you can do outline text. unless you want something rather special, you know, you're engraving wood and you specifically want a shape. If you just want to mark something up for identification, then outline text is the quickest way to do it. This does a nice job. So now we're moving from engraving to cutting. So you can see those little white flashes. That tells me that we've got enough power and that the cut is going right through the material, and the extra energy is reflecting off the honeycomb section behind. Now if we got the fits on this job right, then we might not have to glue it. It should possibly just press together and be good enough to do the job without gluing. Now acrylic is a very notoriously bad material for size. You buy 5mm acrylic and it might be 4.8, it might be 5.2. If it's cast acrylic, it could probably be plus or minus ½ mm, so you could get huge variations in the thickness of the material. Even on a little piece of material like this, you can get probably ½ mm variation. So it's very, very difficult to get good quality fits when you're trying to tongue and groove acrylic. And let's see what we've got. All the parts have popped out. Okay, now we've got our piece of card in, and remember we're setting the focus manually now, so I've got to set the focus back onto the surface with my little gauge. So we need to reset bring the table up a little bit. There we go. I think you can probably see how much quicker it is to just set the focus manually than it is to use the pen pointer, but that's just what I'm used to. You'll notice that wherever possible I'm using radius corners. We'll just strip the protective film off our pieces. Now this is the interesting one, because you can see the way in which the condensate has settled on the outside of the film there. It's even settled on the inside of the components. When we take that off, we're left with the middle of the letters in, which we've got to take off as well. It leaves a lovely clean surface. And across the back of the machine there, we've got some LED strip lighting. It really comes alive. But that's another project. We've got two tongues which point downwards. Well, these tongues here match with it, so we're going to put that one on the tall end and this short one on the short end. And then we're going to find the other side of the ramp, which is here. We're going to drop that on like that, and we'll drop it onto the base. Now it doesn't matter which way round on the base it goes, because it's symmetrical. And there we go, it's plugged onto the base, and the whole thing is actually clipped together very nicely. Now this piece here sits in the middle and points towards the big end. You can put it on that way, but that would be wrong. So what we've got to do is put the slots on here towards these knobs that are on this end. So this is the top of the ramp, and the idea of that is that at this point here, this edge just here, that is the center of the ramp. If we take one of our paper templates that we've made, we will find that we can pop this on here like this and slip it into position. Now at that position there, you'll see that it says 0 in line with the end of this bar. That is the 0 position right in the center, representing perfect focus, and perfect focus occurs on this flat plane here. So we've got a large area here that we can use to set the focus up. Now that's a 4.7mm spacer there. I'm going to use that just as a nominal spacer to start with. Make sure it sits flat in there. There we go. And we're going to raise the table until we get the table to touch on that surface there, just. Touches, it's just grippy down, and there it's loose. So there, that is 4.7 millimeters above that surface there. We can take this out now because we don't need this anymore temporarily. And our focus gauge will sit on here. Now if you look carefully, you'll see that there are slots underneath these tongues which actually cause this to clip down and stay nice and flat. And you know that that's the case because this will just drop down inside these lugs at the end here. So we need to drop it over the lugs and clip it in. And these holes here, these marks on the end, tell you which end is which, because it won't fit the other way. It completely misaligns if you line it up the other way, so it only goes on one way. But there are actually two ways that you can put it on. You can put it on like that and make sure that this end is clipped down, or, and this is a much better way to do it, we can put it on this way. And that is the way that I'd recommend that you use it. Numbers down. You're going to say, well, that's rather strange. Why on earth that? Because I can't see what's going on. Wait and be amazed. Right, so we've got our focus set up with our Z. Now we need to come down here and we'll check power. So we'll set max power. It's set to 20%. I like that. 20% is good. It doesn't matter what power you have it set to, provided it's quite low. Once you've set the power, what we're going to do is play with the speed. So we're happy with the power at 20%, enter. Let's set the speed. Now we've got the speed currently set at 200 millimeters a second. Maybe right, maybe wrong. Let's set it to 150 and we'll see what we get. I'm showing you what I'm going to do here. I'm going to hold the pulse button on and drive it backwards and forwards. I'm going to turn the pulse on and I'm going to drive it towards me at 150 millimeters a second. So this is looking actually quite good, because as we look here, look, you can see the line is thick there. It gets very thin just here, and then it starts getting thicker again. Now that's the thickness of the beam changing with depth. Now what we're looking for is the thinnest possible point that we can find. Now it's difficult to find it here, but let's just turn the paper over and see what we've got. Lift the end out and take it off, and hey, look, we've got a line on the other side. Now that line is actually quite long at the moment. It runs from about 3 at that end to about 2 1/4, maybe 2 that end. Now what we're trying to do now is we're trying to get that line as short as we can, so that we can find out roughly where the most damaging point is. At the moment it's damaging this paper, and I'm using the word damage, you'll notice. It's damaging this paper over quite a long length, but there's only one point, a very short area, where maximum damage will occur. So let's go and see if we can find that maximum damage section. We'll pop that back on again and we'll line this up, and this time I'm going to change the speed up to 200 millimeters a second. Okay, now our results are becoming clearer. Look, we're just about damaging it. We're just coming through. You can see this line here is really crisply clean. This one is just about making it through. And if we look for the point where it starts at around about +0.5 millimeter, and it finishes at just about 1.5 millimeters. So that means our focus point is actually sitting there at about 0.5 millimeter. But is it 0.5 millimeter high or 0.5 millimeter low? Well, bearing in mind that's the top of the ramp with the 2 dots on it. it means our focus point is actually 0.5 millimeter below center. So it means what I've got to do, I've got to lift the nozzle up by 0.5 millimeter to get it spot on. Okay, now we've got this little platform here, which we're trying to establish the gap between the platform and the end of the nozzle. And what I've got here is a little tool that I've made previously, which is basically a 1 millimeter step gauge. And so I can see that it's 1, 2, 3, 4 goes under there easily. What I've got here is a piece of 0.5 millimeter thick steel, very thin piece of stainless steel shim, and I would say I can probably just about get that 4 millimeter step, 1, 2, 3, 4 millimeter step under there. So my guess is that that gap is about 4.4, 4.5. Okay, let's give it one last test and see how we get on. Have we fixed the focus problem? So at the moment, the line looks as though it starts at about 2 and goes through to about 2. So I would say that we're just about spot on with the focus now. We're going to just poke this very soft piece of plastic up inside until we touch the lens. Now, I've got to be very careful, we don't want to damage the lens, so I'm just going to very gently go up until it just touches the lens. And then I'm going to mark it with my fingernail by clamping it just there, and that is the amount that it's up inside. 43.5 plus I think we said 5.5 was the clearance under here. 5.5 48, that's 49 millimeters, which is a strange dimension because they don't make lenses that size. It's got to be 51. Let's take a look at the lens that's actually inside here. Things that don't make sense worry me. I like to understand how things work. I think we'll have that lens out of there and have a look at it. You need to be very careful handling these lenses, and I would suggest you either use the latex gloves that they provide, or I tend to use cotton gloves to handle the lens itself. So we should be able to just undo this with the special tool that's provided. I've just got a natural curiosity. I like to understand exactly how things are and what they are. I don't trust anything. I think you can probably see that in the light, can't you? There's some sort of crap on there. Sorry, debris. Now, you are supplied with a lens cleaning kit and all the instructions. But of course, like most blokes, I'm not reading the instructions. There are two stages of cleaning lenses. One is gentle, and I'll just put some isopropyl alcohol into there, and I use a cotton bud. Just soak the cotton bud in that and very gently. That didn't take much to come off. Right, blow on the lens and you can see that it's come off nice and clear. On the other side of the lens, I can see there is a haze. Can you see that haze on there as well? Let's see if we can get that off. Right, okay. Well, the haze is gone now. And then within the pack that Thinklaser provide, there are these things called lens cleaning tissues. Now, I'd advise you to handle this lens quite carefully because the material that it's made from is a material called zinc selenide, and it's very toxic. You're not protecting your hands necessarily to stop you damaging the lens. I think you're protecting your hands more to stop you absorbing any of the toxicity of that through your skin. The chances are that there is not much there to be exposed to. Zinc selenide as a material is not very good at transmitting the infrared light. It actually is only about 70% efficient. And the reason it's only about 70% efficient is because the crystal structure of the material reflects 30% of the light. So these lenses are covered in a special anti-reflection coating, which you basically mustn't damage, because if you take the anti-reflecting coating off, you reduce the lens to a 70% quality lens, which is useless. This particular lens has got a convex side on the top, it's raised on the top, and then it's very slightly dished underneath. Now that gives you slightly better concentration of the focus point. There's less what they call aberration, which means you get a cleaner focus point. It's slightly better than the simple plano convex lens, but it doesn't matter. When you put it back in, you must make sure that the flatter side, or the concave side, is actually facing the work. So bearing in mind that's the way that the lens tube sits, you've got to finish up with the curved side upwards. So we'll very carefully pop that back onto its O-ring seating, like that. And then I suggest that you don't try and drop this in that way, but what you do is actually put it in this way. Put the lens in and keep it upside down and screw the tube onto the lens. That way the lens will stay flat on its seating. So when it comes to it, you'll feel the O-ring just beginning to bite. Don't over tighten it, just put the smallest amount of tension on it to just feel the O-ring as compressing. Now when you look through it, you should be able to see through the lens like that. Previously I couldn't, it was all cloudy. And that's the sort of thing that I would recommend you do. Probably take a look at that lens once a week, and if you can't see through it, take it out and clean it. And I keep stressing to you, the lens is actually the most important link to make this machine work. Without the lens, you've just got a laser, which does very little. It's the concentration of energy from that lens which is the thing that allows you to do all the work that we do on this machine. I mean, to replace that is probably about 30 or 40 pounds, maybe even more than that. So, you know, you don't want to get through too many of those. They have got a lifetime. You will eventually have to replace it, but I suspect if you treat it well, it'll last you 1 or 2 years. The other aspect of treating that lens well is to make sure that you always have your air assist on. Don't let debris and smoke come up and fume this surface of the lens. You'll see that we've got a hole in there, a mirror, and then a tube that goes right the way down. Well, this is sitting on the end of that tube, so equally well you can get debris, dust, stuff in this end which will sit on top of your lens. So there are two ways that your lens can get dirty, and hopefully you should find that these two shoulders sit against each other. There should not be a gap there. We haven't got an air supply on, so I'll put my air on because that's important. There we go. We should be able to see the line on here now, and it starts at 1.5, it goes through there and finishes up at just about 1.5, so I think we're probably pretty well spot on with our focus now. Well, okay, I've now fitted the 2.5-inch lens which they supplied. I've done an internal measurement which says 56mm. I've got 56mm internally, and 63.5 is the actual dimension, so that's about 7.5mm, and that's 7.8. So that's a reasonable match for the theoretical focal distance. So I'm going to pop that under there, and that works absolutely perfectly. You can hear I've just cut off the air supply. Think back to the logic of what I said earlier. We've got a longer lens. It's got the same amount of power going through the lens, but it'll have probably half as much penetration. So I was using this at 225mm a second to test the 2-inch lens. I suspect I'm going to have to drop this down to maybe 150 eventually, but what we'll do, we'll run it at 225 to start with, just to prove the point of loss of power. And there we go. So yes, as I expected, it hasn't made it through. So we're going to have to drop the speed, and I'm going to drop the speed to about 150. So we could run a bit faster because that's running far too long. I mean, that's running from 3.5, nearly 4, to about 2.5. So that means our centre point is approximately 1 millimetre too high. 0.5 millimetre, 1 millimetre too high. So the way to imagine that is I've got to raise that focus point up to match that one. So I've got to raise the table up. In other words, I've got to decrease the gap to get it to come back down the slope. So I've got to come up about 1 millimetre. So instead of that gap, which is an 8 millimetre gap, I need to go down to something like a 7 millimetre gap. There we go, that's perfect. So that's a 7 millimetre gap now. And bear in mind, this has got a much longer depth of field, so it's always going to have a much longer line. I'm not going to get as much contrast around the middle. But having said that, if we take a look there, it runs from about 2 to 1. So to get that to work, I've got to drop this down 0.5 mil to get that onto its ideal position. So I need to add 0.5 mil to the gap. So to get a 7.5 mil gap, I'll put my 0.5 mil spacer in there, and then we go back to our 7 mil step, which is that one, and I've just set that now to just a snug fit under there. Go down just a shade. 180 millimeters a second, 7.5 mil gap. That means to get that point to here, I've got to raise the table up, which has decreased the gap. So instead of 7.5 mil, it probably is going to be 7.25 millimeters. I don't think we're going to worry too much about that. That's more or less where we expect it. So I'm going to stay with 7.5. Then that's not 56 inches, that's 56 inside, 56 millimeters inside, plus 7.5 millimeters outside, gives me a total of 63.5, which is exactly 2.5 inches. So that one is absolutely spot on. Now I've got something else that I want to try. Now they told me that I couldn't get a 1.5 inch lens. I've modified the inside of this nozzle. It didn't have a very big shoulder in it inside, so what I've done, I've machined it out and I've put a little pressed a teeny weeny ring in there, and that ring is enough to support an 18 millimeter diameter lens. This was the 4-inch focal length lens holder, which had a lens in this back end here. My lens has got to go flat side down inside there, like that. And then on top of the lens, I've got a little compression ring spacer, and that spacer sits against the O-ring to give me just the compression that I need when I close the whole system down. So hopefully I should be able to wind that on, and as I wind it on, at this point here I should just begin to feel the O-ring biting. The lens is not rattling. So hopefully I've got a 1.5 inch lens system now. Whether or not it's going to work and what the dimensions are, but I think if I've got it about right, it should come out approximately 6 or 7 millimeter gap. This lens is going to be very scalpel like. It should give me quite a long cut, or a deep cut, and I may well have to increase the speed quite a lot. Let's increase the speed to 225, maybe we'll go up to 250 even. My calculations and dimensions came out reasonably well, because at the moment, where's it running to? About 1 millimeter and about 1/2 millimetre. So I've got to come up about 1/4 millimetre to get it right. So that's still about 7 millimetres. I think 7 millimetres is close enough. Okay, so I'm going to do the ultimate test of my 1.5 inch lens now that I've just created. And this is something I've done quite a few times this year on my existing machine. Now what I've got here is my pin table and a block of metal with a couple of magnets on it that will actually clamp. This is sufficiently stable that it's not going to move, and I've got this set at the same height as the pins. So I'll drop the paper onto the pins and just drop the magnets on there to stop the paper moving. Now this has come out the opposite way round to what I'm normally used to with my machine, because this has not been written for this machine, it's been written for the opposite hand. Okay, so what we do now, we'll swap that lens over to a 2-inch lens and we'll see what happens with the 2-inch lens. It's doing better than I thought, but the detail, some of the detail is a little bit fuzzy. Some of the very detailed parts are going to overlap and fall. Two and a half inch, it's going to be 7.5. Now the interesting thing here is I'm right up at about 17%, and you can hear that hissy noise that the cutter's making. That's still the high frequency impact engraving zone. Well, it has made it all the way around. We need to go and have a close look at that to see the differences between the lenses. But I think that categorically proves that we've got the 3 lenses now correctly set on focus, because you wouldn't be able to do that unless the focus was correctly set. So we'll just take a look at the results under a microscope. A bit of a serious way of looking at the quality, but we need to do some comparisons so that you can make your own judgment as to which lens you would use for doing a job like this. Now at the moment you don't have the choice of a 1.5 inch lens because they don't make it. I've had to make my own. But I'm sure that in the near future Thinklaser will be providing you with a 1.5 inch lens if you need it. So now we can reflect on the performance of these 3 lenses. Now for comparison, what I've done, I've shown you what I would normally expect from my eBay machine. The first thing I'd like you to look at is up at the top right hand corner. You'll see that I've put an arrow pointing towards the line thickness that each of the lenses produces. As a comparison, we've got a pencil for a 1.5 inch lens, we've got a felt tip pen for a 2 inch focal length lens, and we've got a marker pen for a 2.5 inch focal length lens. So the lines get thicker as the lens gets longer, which is what we said, because the spot size at the waist of the lens is bigger for each of these. When we start doing thicker materials, woods, acrylics, then different depths of field and different power densities have a big effect, and we should be tackling those in a completely different session. For graphics work, where you're working on a surface or with thin material such as paper, you will need the shortest possible focal length that you can get, because that gives you the crispest and the best definition. Well, thank you very much for your time today. We've covered a great deal on lenses, and hopefully this will give you a better understanding of one of the most important features of your machine. That lens is critical to the performance of the machine and the work that you create with it. So choose the right lens and look after your lenses carefully. Thanks for now, and I shall be seeing you next time.